Okay, I'll begin now. So today we'll be learning about momentum. So first we'll learn about what momentum is. So momentum is the motion of a mass. For example, if you have a box and you throw it, then you're moving it with velocity v and mass m. So it will have momentum, which can be written as mass times velocity. And over here you can see that momentum is a vector because velocity is a vector, so it's gonna have direction as well. And the unit would be mass, which is kg, and velocity, which is m over s. So that's the unit for momentum. Okay. So this is an example of momentum. If the teddy bear is going down and is moving downwards and the ball is moving downwards, then it will have the teddy bear, first of all, after it goes downward, it's gonna stay there, and the ball is gonna bounce back up if it's a bouncing ball, for example. So if you're trying to find the change momentum, then it would be delta p, which would be delta m times v. And you can also write that as p final, or momentum final minus the initial momentum. So for example, the bear, since it's going down, it's fine and it stays at rest in this picture, then you can assume that the final momentum would be 0 and the initial momentum would be mass times negative velocity, again because momentum is a vector, so and the velocity is going downward, so it would have a negative velocity, so it would equal 0 minus negative mv, which is just mv. And that's a change of momentum. But for the ball, since it's going down initially, it has initial momentum. And since it's bouncing back up, it has final momentum. So it would define, first of all, the initial momentum would be m times negative v as well, since the velocity is also going downwards. And the final momentum would be m times positive v, since it's going upwards. So if you subtract those two, you get you would get mv minus negative mv, which would just be 2mv. So you can see that the ball has more momentum than the bear. Okay, so now we'll talk about impulse. So impulse is the force being acted, the force you apply for a certain amount of time. For example, if you're playing baseball or something, then and a ball is coming at you, then you would hit the ball with a force over a certain amount of time to get the ball to move somewhere. And that would create an impulse. So the definition of impulse is force times the change in time. And impulse, like momentum, is also a vector since force is a vector. And even though the time's a scalar, it doesn't matter since force is already a vector. So impulse would also be a vector. And since the unit for force is newtons and the unit for time is seconds, the unit for impulse would be newtons times seconds, or kg times mass over seconds. Okay. Oh, another thing is, if you, since like impulse is force times time, then if you exert a large force over a small period of time, it would be the same as exerting a small force over a long period of time. So that's something to keep in mind. So now we'll talk about the impulse momentum theorem. And the impulse momentum theorem is how the impulse is equal to the change in momentum. And you get that because since impulse is equal to force times time, and force is equal to ma, a can also be written as the change in velocity over the change in time. So if you plug it into the equation again, you get mass times delta V over delta T, and then times the other delta T. And you can cancel out the delta T, so you'd be left with I is equal to M times delta V, which is just the change in momentum. So that's how you get the equation. Impulse is equal to the change in momentum. Okay. And now we'll talk about the conservation of momentum. The conservation of momentum is when the total momentum of a system is conserved. And you also derive this from the impulse momentum theorem. So if you write impulse is equal to delta P, or P final minus P initial, you would write force times delta T is equal to the final momentum minus the initial momentum. So when the system is conserved, then the force is going to be equal to 0. So there's like no external forces acting in the system, which is right here. So if you cancel out force, then you're left with this side of the equation equal to 0. So it would just be P final minus momentum initial is equal to 0. And you can write final momentum is equal to initial momentum. So, and that's how the momentum, conservation momentum is formed. The initial momentum being equal to the final momentum. And if a system has more momentums, then you can just add the final momentums and the initial momentums together. And you can also write expanded form like this right here. So it would be, this is say the initial momentum, and this would be the final momentum. This the, if there's like another momentum, then we read that and that. Okay, so now collisions. So there are two types of collisions that are elastic collisions and inelastic collisions. So what makes these different is in this first picture right here, this is an elastic collision because well, for collisions in general, the momentum is always conserved, but for what makes them different is that elastic collisions have conserved kinetic energy as well. So these two, for an elastic collision, these two balls are going at each other, and then after the collision, they bounce back. But for an inelastic collision, this train right here is not moving, and this train right here is moving at it. So after the collision, they both move together. So so the collision for an inelastic collision would make the energy, kinetic energy, not conserved, because if you write the conservation momentum for both of them, for example, the first one, it would be ma times v initial is equal to mb times v is negative. And for this one, since like after it's connected, this initial would be ma times v initial plus 0 is equal to, and then the final would be that mass is added together since they're both moving times the v. Because they're moving together, they have the same velocity and their masses are added together. But before that, it's just this one has momentum and this one's 0 since there's no velocity. So since it has ma plus mb, then their kinetic energy couldn't be conserved. Okay, so we can move on to question 1, which I'll give you 2 minutes to do. Okay, so I'll explain the first question now. So since uh, in this question you're using conservation momentum, and since a 2030 kg car is traveling 30 miles, meters per second, and v is 30 meters per second, and another car with 202 kg is at rest, so the v is 0. And it says the bumpers lock and cars move forward together. So you can assume that this is an inelastic collision. So you would write M1V1 plus M2V2 is equal to M1 plus M2 times V, since the masses are together and they have one velocity. So you can plug in what you have. You have 2,200 times 30 plus 0 is equal to 2,200 plus 2,200 times V. And then you can just solve for V. Okay, so this is the solution. Okay, so problem 2. Okay, I'll go over the problem now. So a 10 kg ball is moving at 13 meters per second at a 20 kg ball that is at rest. So the V is 0. After the collision, the 10 kg ball is moving with a velocity of 7 meters per second. What is the velocity of the second ball? So this is an elastic collision, which is when the balls aren't together. So it would be m1 v1 plus m2 v2 is equal to m1 prime plus m2 v2 prime. So the first mass we know is 10, and then velocity is 13, plus 0 is equal to 10 times 7 meters per second plus 20 times v, since we're trying to find the velocity second ball. So again, you can just do the math for that and then find v. And you get this solution here. Okay, so move on to question 3. I'll go over the problem. So a 0.25 kg ball strikes a 1.25 kg ball at rest. So it would look like, and then after the collision, the 0.25 kg ball is moving with a velocity. Oh, also for the first one, we don't know the v. So after the collision, the 0.25 kg ball is moving with a velocity of 18 meters per second, and the second ball is moving with a velocity of 9 meters per second. So we can say that the ball goes like this way and this ball goes that way. So we can write 0.25 times V plus 1.25 times 0 is equal to 0.25 times 18, and then plus 1.25 times 9. And again, you can just find the velocity by doing it. And here's the solution right here. Question 4. Okay, I'll go over the question now. So the question asked you which of these would not be an example of an inelastic collision. And if you go to options, you can see that in the last one, it does say that the kinetic energy is conserved. And we know that an inelastic collision cannot have energy conserved, and elastic collision can have is the only one that can have kinetic energy conserved. So the answer would be the last one. So here's the solution. Okay, so next question. Okay, I'll explain the question now. So it gives you that the mass of the marble is 0.1 kg, and it falls off a bed with a height of 1.2 meters. And it asks you what is the impulse of the marble as it hits the ground. So, the impulse equation is I is equal to force times delta t, but um, you can also write that as from the impulse momentum theorem as delta p, which is final as p initial. So in both situations, we need the velocity, but actually the initial momentum is zero, so we would just need mass times the final velocity. So we're trying to look for the final velocity. And if you remember from last week, I talked about the energy conservation, which is the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the final potential energy. So we know that the initial velocity is zero, so initial kinetic energy would be zero, and after it hits the ground, the potential energy would be zero because there's no more height. So you're left with initial potential energy being equal to the final kinetic energy. And you can write that as mass times gravitational acceleration times height initial is equal to 1/2 m times the final velocity. And you can cancel out the mass first, so you're left with g times h initial equals 1/2 final velocity squared. And you can cancel, and you can times 2 on both sides and to get final velocity squared equals 2 gh, and final velocity is equal to root 2 gh. And we know that the height is 1.2 meters, and we're given that the gravitational acceleration is 10 meters per second squared. So you can write 2 times 10 times 1.2, and then you can get the final velocity from that. And then after you get that, you can just plug it back into the equation of the impulse to get mass times final velocity. So the mass is 0.1 kg, and then times to 1.2, and that's the impulse. You guys understand this one? And this distribution right here. Okay, so moving on to the next question. Oh wait, this one. Okay, I'll explain the question now. So it says the block has a mass of 20 kg and the angle here measures 50 degrees. And there's no friction between the block and slope. And it asks what is the momentum after its traveled a horizontal distance of 10 meters. So we're trying to find the momentum. So you need to find velocity because you're given the mass. So again, you can use the um conservation of energy. So it would be initial potential plus initial kinetic is equal to the final potential plus the final kinetic energy. So again, the initial kinetic energy is zero and the final potential energy would be zero since there's no velocity at the top and there's no height at the bottom. So it'd be mass times gravitational acceleration times the initial height is equal to 1/2 m times v final squared. And again, cancel out the mass. So in this situation, you can write that like we found on the last question. And we don't know the height actually when we're given the horizontal distance, but we are given the angle. So if you guys know tangents already, you would know that tangent 50 degrees in this situation would be equal to the height over the horizontal distance, which is 10. So we can find that height is 10 times tangent 50 degrees. So I'm not going to solve it right now, but 10 tangent 50 degrees, and then you plug it back into this equation and then solve for the final velocity. And then after you solve for the final velocity, you just plug it back into the equation and get, since the mass is 20, so it would be 20 times the final velocity, which is over here. You guys understand this question? Okay, so this is the solution. Okay, so question 7. Okay, so I'll explain the question now. So Joe with mass 90 kg jumps straight up. To do so, he bends his knees and produces an upward force that results in a constant upward net force of 100 newtons. If Joe experiences his force for 0.9 seconds after leaving the ground, what is his velocity after he leaves the ground? So, you're given the mass, force, and time. So you already know that you can use the impulse momentum theorem. So it would be force times the time equals the final momentum minus the initial momentum. And the force is equal to 100 newtons and the time is 0.9 seconds. And since he's going upwards, his initial velocity is going to be 0. So it's going to be mass times the final velocity. And you know that the final velocity is, the mass is 90 kg, so it'd be 90 times the final velocity. So you get the final velocity is equal to 100 times 0.9 and then over 90. So it would be 90 over 90, and that's just 1 meter per second. So that's how you get the velocity. Okay, so this is the solution here. Question 8, 9, 10. So you guys can have like 5 to 8 minutes to do this. Okay, so I'll go over the first question first. For question 8, it asked, you are lying in a bed and want to shut your bedroom door. You have a bouncy ball and a blob of clay, and both of the same mass. Which one would be more effective to throw at your door to close it? So if you think about it, when you throw a bouncy ball at the door, it's probably going to bounce back. So you can assume that the bouncy ball will create an elastic collision, and the blob of clay, it probably is gonna stick to the door as it keeps moving. So it's gonna be an inelastic collision. So for the bouncy ball, it would be, if you throw it, it could be M1 times B1, and the door, like initially, it's could be static, so the momentum will be 0, so it's going to be plus 0, and then it's going to be M1 V2 plus M2 V3. So this is the velocity the door is moving. This is the mass. This is the velocity the bouncy ball has when it comes back, and it's the mass. And another thing to note is that the velocity, since it's coming back, is going to be negative, since it's bouncing backwards. It's going to be negative V2. So you can write it as mass 1 times V1 is equal to negative M1 V2 equal to M2 V3. So if you move this to this side, it'd be M1 V1 plus M1 V2 is equal to M2 V3. And then this would just be, actually, the velocities, you can assume the velocity that the bouncy ball goes, that you throw, will be the same when it comes back. So these two velocities are to be the same. So it'd be 2m1 v1 is equal to m2 v3. So v3 is equal to 2m1 v1 over m2. And then for the blob of clay, it will also be m1 v1 plus 0. And then since it's an inelastic collision, the two masses will stick together. So it'll be m1 plus v2 times v2. So, and then you can find v2 is just m1 v1 over m1 plus m2. So if you look at these two velocities, you can see that the bouncy ball would be more effective to close the door since it has higher velocity. Okay, I'll give you another another minute to do question 9. Okay, so I'll go over question 9. So a man with a mass of M is painting a house. He stands on a tall ladder of height H. He leans over and falls straight down off the ladder. If he's in the air for S seconds, what is his momentum right before he hits the ground? So it's basically asking for his final momentum. And since you're giving us seconds, he's in there for S seconds, you can use the impulse momentum theorem. So it's P final minus P initial. And you know that his initial momentum is zero since he's leaning over an impulse, so he has no velocity, and then his impulse is force times delta t is equal to the final momentum. So the t is s seconds, and then the force, since the only force acting on him in this situation would be gravity, it would just be mg being the gravitational constant. So the final momentum would be mg times s. Okay, so that's gonna do it for this lesson this week. So have a good weekend, guys.